Wi-Fi. Leave.
Leave.
Leave. Leave. Why are you even here?
I have class.
So what?
Don't you got class?
Yeah, this is the office. Go away. Go in your room.
The Wi-Fi's so bad.
So what? You think you have Wi-Fi?
You don't give me no Wi-Fi. You don't give me your phone, man?
No.
So you shut up then.
You can use your own Wi-Fi.
It's bad in the wrong.
So you don't buy Wi-Fi.
Lecture on the Jovian planets, and I was about to talk about the rings. Just to finish off this lecture, are there any questions before I get started? So all of the Jovian planets have rings, and there's a number of proposals for their creation. I mean, we know that they all occur to some degree, but we actually don't know what is the dominant mechanism for each ring system. I'll talk about the Roche limit in a second. That's the fact that there is a point where you get so close to a planet that if you have a loose rubble held together by gravity, so an asteroid generally that's kind of a loose collection of rubble, then it'll get ripped apart by the tidal forces. That's called the Roche limit. So that is one mechanism by which you get this debris around large planets that have large tidal forces like the Jovian ones. You also have, anytime you have a big impact, like a meteor impact, right, you get debris that's released, and that kind of happens continually, right, around planets, creating a bit of a ring system. You similarly have maybe not something totally destroyed by the tidal forces, but it can also just generate debris. And then we know this occurs for Jupiter's moon, Io, which is very volcanically active, right? Its volcanoes actually release a material that then becomes part of the ring system. Okay? So all of those are in play. Probably one of the largest features is the Roche limit, which I'll talk about. And then I'll also talk about just some of the things that affect the structure of the ring system, and particularly Saturn's rings have got like a very characteristic look to them. Okay. So one thing to talk about is the Roche limit. This is the fact that there are a number of tidal forces. Like think of the fact that we have tides on Earth from our moon. That's because, remember, one side of the Earth is tugged on more strongly because it's closer to moon, so gravity is stronger compared to the other side. And what that means is that the oceans are pulled toward the moon, and that's what generates the tides. Right? The Earth is rotating, so once a day, or twice a day, both the side towards the moon and away from the moon. As you rotate through a bulge, a tidal bulge, where the ocean is higher, and a tidal minimum where the ocean is lower. In any case, these tidal forces work not just on oceans, but also just on planets or collections of rubble in the case of small asteroids. And it squeezes and pulls, and if you're too close to a large planet, having large tidal forces, it'll actually rip apart any pile of rubble that would otherwise be held together by the small amount of gravity that a little pile of rubble has. That's called the Roche. So if you get too close to like Jupiter's large, has really strong tidal forces, it'll start to rip apart lots of asteroids. Now some don't get ripped apart, like solid iron asteroids, but a lot of asteroids are little piles of rubble, and they'll get ripped apart. Okay. And so this occurs to some degree for all of the Jovian planets. So of course the most beautiful ring system is on Saturn. Again, they all have rings, but Saturn has the most prominent. And we don't know exactly why Saturn has such larger ring systems. And it's actually debated whether Saturn has always had these rings, or maybe it's just a transient phenomenon. Maybe a large object went inside Saturn's Roche limit, generated these rings, and they'll go away for a few million years. Okay, that's a prominent theory. Here's a beautiful picture, by the way, of Saturn eclipsing the sun, so the sun's behind Saturn here, so we get a really nice view of its rings. And you see that they have some structure. So one thing that causes structures are called shepherd moons. So here's one of the smaller moons of Saturn, Daphne, is here kind of shepherding, it's kind of carving out a lane. It's kind of shepherding, we call it gravitationally. It's created, you actually see little waves being created as it passes above and below the ring system. In any case, so when you see these rings, one feature that causes little gaps are these little shepherd moons, we call them. Another is the what are called orbital resonances. So here's a picture of the ring system going from Saturn on the left to the right. You see, we give names to all of these to areas on the rings. So they have these interesting structure with these little gaps. And one of the things that causes these interesting little gaps are what's called resonances. Now we've seen these in the planets, but in a ring system, you have, so remember that just due to Kepler's laws, the further you get from a planet, the slower your orbit, right? So you're orbiting quickly, and so this ring system, first of all, it's mostly ice, but it has colors because it's dusty ice. But this, it's all these little clumps that are generally pretty small. The thickness of the rings goes from like 10 meters up to about a kilometer. Not thick at all, very thin. So less than a kilometer of just rocks and dust, boulders, all pretty small, all less than a meter in size. And these little clumps of stuff are all orbiting faster, closer to the Saturn, and slower, further away. And you'll have certain speeds where that you get what's called a resonance, where you get some clumps orbiting at some distance, orbiting at exactly 1 revolution for every 2 revolutions somewhere else. That's called a resonance. What that means is that anytime you complete 1 revolution here, you complete exactly 2 revolutions here, so you line up in the same place over and over and over again. And that tends to kick you out of your orbit. Because if you keep lining up in the same place, then you're going to be attracted gravitationally. So there are certain distances from Saturn where things orbit at just the right speed that they get kicked out by what we call resonances. So these produce what we call Kirkwood gaps. So like there's a gap here, gap here, gap here, and so on. These correspond to resonances. I said also some gaps though are produced by shepherd. Again, as I said, the origin of these rings, there's no consensus of whether these are old or new. It's likely that all these large planets have some degree of rings due to, for example, continual asteroids getting ripped apart inside the Roche limit, but maybe just a really large amount of debris happened to occur 100 million years ago, and it's going to dissipate, and Saturn may hide in a few 100 million years look, say, like it has the ring similar to Jupiter. We don't know. Here's an artist's illustration of what the debris in the rings might look like. Again, it's very ice rich. It's comet-like stuff, but it's all mixed with dust, so it has color. But we've never gotten so close that we've seen this. We have to have artist's impression. And again, even though we've sent satellites to Saturn, we haven't gotten this close because Saturn's huge. It's easy to forget. When you're flying by Saturn, you see these beautiful pictures of the rings. You are like still like 100 Earths away. That's how far you are because of how it just looks like you're close. Saturn is really, really large. So I'll just complete this lecture with just showing some rings of the other planets. So here's Jupiter's rings. You have fuzzy pictures like this, but it's hard to get a good picture of the rings because they're so faint. Mostly made of it's just a thin ring of dust. Here's the rings of Uranus. Here you can just barely make out that there are also gaps and some structure to the rings of Uranus. But being even further away, it's even harder to see these rings. There's another picture where you kind of see these Kirkwood gaps showing structure to the rings of Uranus. And then finally, Neptune also has rings. And here again, it's a composite image, so it looks kind of funny. That's because in order to get a good picture of the rings, you have to take kind of a separate long exposure photograph and then stitch them together. We'll actually talk a little bit more about the Kirkwood gaps in the next lecture when we talk about asteroids. But I'll just round out this lecture by asking a question, something that I just covered. on Saturn's rings. So I just want you to know how thick, roughly speaking, how thick are Saturn's rings? Watching the ball. Ten more seconds. Okay. All right, most people got the right answer. Just they're very, very thin. Remember, just like a 10 meters to maybe a kilometer. Very, very thin. Remember, Saturn's big, so the rings are so thin. If we see them edge on, we can't even see. Okay. Are there any questions about the Jovian planets, ring systems? Okay. If not, we will talk about. We'll move on to the next lecture, which is. I think it's numerically, I have it as lecture 14. This is a lecture on asteroids. So we're kind of rounding out our discussion on the solar system. We talked about the inner terrestrial planets, talked about the outer Jovian planets. Okay, we talked about their moons. And remember, there's all this other debris in our solar system. There's not just the big main planets. There's all the stuff that never formed planets. There's dust. There's little clumps of rocky material we call asteroids. There's little clumps of icy material we call comets. Okay. And then there's even things that are very large, like Pluto, that we now call dwarf planets. So, first of all, just an overview of our solar system includes not just the planets, but remember, between Mars and Jupiter, there's something we call the asteroid belt. That's where most of the rocky material in our solar system, most of the terrestrial material that never formed planets, still is. That's where a lot of the asteroids are, an asteroid belt. And that's like a giant ring. He's talking about ring systems. It's just like a giant ring, and our solar system never clumped up to form a planet. Okay. We also talk about the Kuiper belt. That's the belt past Neptune, where there's also a lot of debris, including Pluto. And this is more ice-rich. This is where a lot of comets, cometary material are. But then there's also where a lot of the comets come from that make it into our inner solar system, because the Kuiper belt, most of that stuff stays in the outer solar system, the belt. But the stuff that wanders into our inner solar system that make these beautiful comet displays every 100,000 years is called the Oort cloud. That extends far beyond the Kuiper belt to the edges of our solar system. It has randomly moving debris, not just in a clean ring or belt. Okay, so we're going to talk all about this stuff today. Now, it's not just, when you think of asteroids and comets, it's not just big boulder-sized things, and it's not even just pebble-sized things that we're talking about. It's also just dust, right? So the solar system is filled with gas and dust, and we can actually see dust. It's called the zodiacal light. There is near the Earth kind of a large cloud of dust. It's like a pancake-shaped cloud, and it's kind of continuously replenished by disintegration of comets and asteroid collisions. Most of which is coming from Jupiter area, comets from Jupiter, and this is all very small, so dust. So in the region, size of millionths of a meter, so little grains of dust. So here's some pictures of this diagonal light, that yellow glow. But when we think of asteroids, we're normally thinking of something a little bit larger than just dust. We live in a wonderful age where we now have actual pictures from missions, even some video where we have landings on asteroids. So these are just rocky bodies, often held together by gravity, but very loosely because they're so small. We don't have a lot of gravity. Here's a rover that landed on an asteroid called Ryugu. And you can see it's kind of jumping around. That's why it's a little blurry, but it's like an amazing kind of photograph. Here's another example. Let's see, I have a video link. Click on these. Here. Yeah, so here's a video of a rover landing on this kind of rubble pile asteroid. Absolutely amazing. So it actually, right, so it landed and then kind of took off again. And you see all that rubble, because it's very loosely held by gravity, kind of exploding outward. That's really amazing. So asteroids, these are relatively small, rocky objects. So this is terrestrial material, metals and rocky stuff that the Earth is made out of. But we can say they're leftover rocky planetesimals. They never formed planets, right? Remember, there was this process of accretion where you have this stuff that gravitationally formed the planet and then kind of slowly grabbed, kind of gobbled up all the stuff in its lane. So like the Earth, right? There's not a huge amount of asteroids around Earth because it gobbled up stuff. So when you're talking about the asteroid belt, there's a region where there never formed a planet between Mars and Jupiter. That's where most of asteroids are. They form like this distributed belt. They never clumped up to form a single planet. And the total mass, just to give you a sense, you know, there's a lot of asteroids, but the total mass is much less than the mass of the moon. And that's in our whole solar system. The very largest one is called Ceres. I'll show a picture in a bit showing how big it is relative to the moon, but it's almost 1,000 kilometers across. Here's the second largest one shown on the left, called Vesta. There's more than 1 million that we've identified greater than 1 kilometer in size. So there's more than 1 million pretty large asteroid objects, and we keep cataloging more. We've cataloged more than 500,000. They're very hard to detect because they're so small, but we keep adding to our inventory and we keep track of them. One neat thing is that before the invention of iron smelting, which is difficult, it's difficult to learn how to heat rock up enough to melt out iron. Meteorite, like iron from meteorites landed on Earth, you can dig these up and you have solid, pure iron in some of these iron meteorites. These were the main source of iron before the invention of iron smelting. Like so, in the Bronze Age, all iron is meteoric. So you see these daggers, like Tutankhamun's dagger in 1300 BC. You can tell it's made of meteor iron. Okay. This is the time because it's easier to melt and find bronze than iron. So there's a period called the Bronze Age before we had learned to smelt iron. Here's a beautiful slice of an iron meteorite where it has what's called a Widman's pattern. This can only happen in meteors because it takes, in order to form this particular crystal structure that you're seeing, that's very beautiful. Those crystals can only form if you let the iron cool off in outer space very slowly over millions of years. So it doesn't happen on Earth. So that's one clear sign that you're looking at iron from a meteorite. This is an example found in Iowa, 1976, called the Alford meteorite. So how do you find asteroids? Well, you use telescopes that see, a little glinting thing across the sky, and you use telescopes at multiple locations to use parallax. Remember we talked about parallax? That is, if you're looking at something from 2 different locations, you see it shift relative to the background stars in the sky. So here's an example, right? You're looking, say, from the left, and you see something with a star over here in the background. But if you look at that same object from the right, the star is now shifted relative to it in the background. So here's an actual photograph, right? So you're taking a long exposure photograph of an asteroid moving across the sky from one telescope highlighted in green, from another telescope highlighted in red. So we see there's what's called parallax. And this is the same principle, by the way, that our eyes use to see things in three dimensions, right? You have one eye seeing things at a slightly different angle from the other eye. And your eyes put them together to figure out how far away something is. We use the same principle to figure out how far an asteroid is. That's how we can tell, right? Tell how fast it's moving from how fast it moves across the sky and how far away it is. We can then
What are you doing?
figure out its trajectory, figure out where it came from, where it's going, whether it's going to hit the Earth. And in this wonderful age that we live in now, just actually been able to send missions to asteroids, including the scoops on asteroid material up and down back to Earth. I'll show you a couple of examples of pictures a second ago. I'll show you some more. The largest asteroids have been known for over about 200 years or so. The first asteroid to be discovered was the largest, which is not surprising because it's easiest to see. It's Ceres. That's shown here. It's about 1 kilometer across. You'll notice, by the way, that so this list of the largest asteroids by diameter, all of them are between about 2 and 4 astronomical units from the Earth. In other words, they're between the orbits of Mars and Jupiter. So these are all from the asteroid belt. You see the second asteroid discovered was, well, okay, this is the 4th asteroid discovered, but it's the second largest. That's good. So here you can see the relative sizes. So there's the Earth, the Moon, and Ceres to show you how large the largest asteroid is. You can see that it's pretty round. It's large enough to actually become spherical. Unlike the second largest, Vesta, which you can see is a little bit potato shaped. It's not perfectly spherical the way Ceres is. As such, Ceres is large enough to be classified as a dwarf planet. The largest asteroid, actually, we call it a dwarf planet, but it's amid all this other debris in the asteroid belt. Both Ceres and the second largest asteroid, Vesta, were large enough that they could undergo differentiation. That is, from the early system, early solar system, they were a big molten block, and heavy stuff went down to the center, lighter stuff went out to the top. So it has, if you did a cross section of
What are you doing?
largest asteroids, they would look like those cross sections of the Earth, where you have a mantle and a core.
When is mommy coming?
She just went out, man.
And that's, by the way, we'll talk about that's the origin of the difference between stony meteorites and iron. Sometimes you get an iron meteorite, which is a core, differentiated asteroid. Sometimes you get a stony meteorite, which is like the
没有虫妹的，
undifferentiated
我
asteroid.
有肉。
We call an undifferentiated asteroid. One
I like
that
watching this
is large enough to go through differentiation.
There's nothing in there, no?
So I do want you to have a rough understanding of how big the biggest asteroid is.
Yeah.
Ceres,
I'm
I
gonna
want you to know, is about
No! Leave it!
Looking at the Mandy. Why should I leave?
What?
and here, so this is
Huh?
Ceres. Here's just a bunch of photographs of the smaller asteroids in order. So Vesta is the second largest, third largest, and so on. And you see that after Ceres, which is
Go away, go away, go away!
potato shape, that's because gravity is less strong.
You don't know who he represents. He's the librarian.
Irregular potato shapes. There's some other nice pictures of various asteroids. You really get a sense that they've been, one reason they are potato shaped, in addition to just gravity not doing its job, is you can kind of tell that they've been bashed, they've been battered by other impacts. Like here, it kind of looks like a crater from two asteroids hitting each other. And sometimes you get these interesting like rubble piles. So here's a rubble pile where it's very irregular shaped. This is an example of a rubble pile where it really is just very loosely held together by gravity. Eros. This is not a rubble pile. This is clearly kind of a looks like mantle-like material, but it's battered and potato shaped. So I do want you to know why small asteroids are not spherical in shape. It's because the strength of gravity is less than the strength of rock, essentially, right? So on something large like Earth, right, you can have a mountain that's fairly large, but gravity is strong enough that you can't make a mountain too high or else it'll just crumble, right? The strength of rock is not large enough to be more than a tiny, tiny fraction of what Earth's dynamic. The same is true of asteroids. You get small enough, there's not much gravity. So the
What
strength
are
of
you
rock
here
will
for?
pull
Go
together.
in the room, you chunky cheeks.
No.
No?
Now, when we look at asteroids, all we see is this little flint, right?
No, you're not.
It's small.
No,
You know, unless we see
no,
that
no.
photographs.
Just stay in the room, Lahaya. You're already wet in the room. Just stay in there.
Across the heavens. So really the only way we have to categorize them is by how shiny.
Why don't you come out here when I'm gonna be turning on my cam?
It's a perfect absorber, something that's dark,
Huh?
has an albedo of 0, whereas something like snow has a close to 1. And when we look at asteroids, the different composition reflects
Say hi, Ma.
color, albedo, right? So like iron has a different albedo than a rubble pile. Okay, so this
Stop! I'm gonna kill you.
You know downstairs open, right?
is the rich C-type.
Go downstairs. Beat it, folks. Open the door.
These
Go.
are mostly
Get down.
basically
I got mine now.
piles
Not yours
that
anymore.
rest over
Downstairs open.
Oh, you're gonna hit me?
Just shut up, Papa.
This is an example.
You're falling, eh? Why?
It's so large.
No,
Most of
whatever.
these
Stay there.
asteroids are C-type.
Okay? Stay there. Yeah, do stay. Stay.
These are fairly dark.
You're not allowed to
Go
go.
in the room, Ma.
No. You stay here.
S-type,
We're not leaving.
silicus, or stony, make up about 17% of known
Go
asteroids.
away.
No, stay.
Hurry up. Hurry up.
Iron,
Stay.
magnesium, silicus.
Shut up, Ale. Go.
These, when you think of an asteroid,
Yeah, I'm saying,
maybe that obviously a metallic asteroid.
You're stupid.
If they make it through, that big chunk of iron can make it down to the Earth without breaking apart. These make up about 10%.
Your music too loud.
Metallic fragments of what were initially iron nickel cores of differentiated objects, things right where that iron all smelted down when it was hot in the early solar system. These, because they're kind of shiny, because they're metal, these have higher albedo. And where are the asteroids? Well, here's a picture showing the inner solar system where you have the sun in the middle, of course, and then Mercury through Mars. And then most of the asteroids you see are in this, what we call a belt. So this is a picture that shows what we've tracked, all the asteroids in the inner solar system. And you see there's a few here near the Earth and near the sun, but almost all of them are in this belt. Okay. Here's Jupiter. So another large source are, besides the belt, the next largest source are actually in the orbits of Jupiter, just trailing and ahead of the orbit of Jupiter. We call these the Trojans. So those are highlighted in green. And then we also track near-Earth asteroids. So, like I said, there's not so many near-Earth compared to the asteroid belt, but we've tracked more than 18,000 of them. And we're concerned about those, of course, because they could hit the Earth. Right? I'll talk more about that near the end of the lecture. We subcategorize near-Earth asteroids into ones that tend to stay outside, just outside the Earth's orbit, or stay just inside the Earth's orbit. These ones that are have asterisks are ones that can cross Earth's orbit, so potentially hazardous. If we look at, so here the x-axis here is distance in terms of astronomical units. So here's the Earth right here, and here's Jupiter out here. This shows you how many asteroids there are as you move out from the sun. And you see there are some near Earth, right? Those are near Earth asteroids. And you see there's some near Jupiter, right? But the vast majority are between Mars and Jupiter. So here's Mars. So you see there's not too many near Mars either, but just outside of Mars, you start having a huge number of asteroids. So this here is the asteroid belt. And you see some interesting features. You see gaps. Okay, this is why I said I'm going to talk about Kirkwood gaps again. You see a big lump of asteroids and then hardly any, and a big lump of asteroids and then hardly any. This is fascinating because this is due to resonances. Okay, I'll talk more about this in a second. First of all, though, we can add a little bit more detail to this plot by adding on the y-axis the orbital inclination. So these are all, we would call them in a belt because they're mostly in the ecliptic. Okay, but if you want to add the detail of how far out they're inclined out of the ecliptic, we have a nice plot like this that shows that most of them are within 10 degrees of the ecliptic. So most of them are like in a belt, like this much within the ecliptic. But there are some little regions that are up to like 20 degrees outside the ecliptic, something like that. And we have names for these. If we zoom in just into the main asteroid belt between 2 and 3.5 astronomical units, you know, we have all of this detail that we've cataloged, and we give them names like belt A through G, similar to we give the rings of Saturn. And you see, you know, so here's Ceres is right here. Here's Vesta, and here you see very clearly, and colored them, but you see that the belts are separated by these gaps. There's a gap here, a gap that's hard to see here, a very clear gap here, and so on. So I'll talk about the gaps in 1 second, but I do want to round out this discussion by talking about the Trojans. And the Trojans are the ones in the orbit of Jupiter. Now, it's kind of an interesting astronomical fact that I haven't discussed so far in this course, that anytime you have a planet orbiting the sun, there's a couple special points around the orbit called Lagrangian points. So here's the sun, and here's a planet orbiting the sun, where you can be in that orbit and the tug from the sun and the tug from the planet kind of cancel out and create kind of a nice stable little region where you can accumulate stuff that doesn't get tugged away. And so you have these Greek asteroids, we call them, in the L4 points. It's just ahead of the orbit of Jupiter in its orbital path. So they kind of stay in this orbit just ahead of Jupiter as Jupiter orbits the sun. And you have the Trojans, we call them, just behind Jupiter. And the Greeks are 60 degrees ahead of Jupiter's orbit, and the Trojans are 60 degrees. So that's why you see in this picture, here's Jupiter, you have the Trojans just behind, and the Greeks just behind. Right, so it's another sort of thing I have on the list of things for you to know. You know, where are the Trojan asteroids? Well, they're all, when we talk about asteroids, we're talking about between the orbits of Mars and Jupiter, but including the orbit of Jupiter. And the Trojans are in Jupiter's orbit, 60 degrees ahead and behind. Okay. Specifically, right, we have an additional name, but we call all of these the Trojans, but the Greek specifically are the ones ahead, and the Trojans, sometimes we say are the ones behind. Now, there's a question, where did all these asteroids come from? Why is there this huge region, right, just with asteroids? And, you know, one of the first suggestions, one of the first kind of obvious thoughts is that there was a big planet that should have formed there, but got kind of broken up, right? This doesn't really work because, remember, if you add up all of the mass of the asteroids, it's a much less than the mass of the moon. In fact, it's about 4% the mass of the moon. So that doesn't quite work, right? There can't be a huge planet there because it doesn't add up to a big planet. There's also chemical differences between the asteroids, suggesting that they kind of just came, they didn't come from one particular source. But this is where the story of things like Kirkwood gaps come in, because Jupiter is a really large planet. So it has really strong tidal forces, and also just in general affects the orbits of things near it. So I think a major theory here for what happened to this asteroid belt is that Jupiter is large enough that it kept little planetesimals like Ceres and Vesta ever accreting to form a planet. And this is primarily through orbital resonances that generate these gaps. The same way there are rings in the gaps of Saturn, there are rings in the asteroid belts. There's these gaps due to resonant orbits, because Jupiter has a really strong gravitational pull, and if you go a certain distance out in the asteroid belt, you'll do like one orbit for every some number of orbits of Jupiter. You go a little bit further out, you get another number of orbits for some number of orbits of Jupiter. And that means that at these particular points, in these what we say Kirkwood gaps, any orbit of, say, Vesta or Ceres or any asteroid in this belt will become aligned with Jupiter every some number of years. And that'll tug them in the same direction over and over again, almost a resonance, until they get flung out. So we can actually show you these resonances. So here again is the distribution of asteroids between Mars and Jupiter. And you see one of the main gaps is a place where an asteroid does 3 orbits for every 1 orbit of Jupiter. That's what that 3 to 1 means. Okay. And in that region, right, every 3 orbits of an asteroid, you align exactly with Jupiter again, such that you keep getting tugged in the same direction until you get pulled out. There's another gap that happens to be at a resonance for every 5 orbits of an asteroid, you have 2 orbits of Jupiter. Okay? There's another gap where for every 7 orbits of an asteroid, you get 3 orbits of Jupiter. There's another one whenever there's 2 orbits of an asteroid for every 1 orbit of Jupiter. Okay? And so you can see what's happening is you keep getting disrupted and pulled and tugged by Jupiter's strong gravitational field. And that prevents all of this material from accreting to form a single planet. You keep getting kind of tugged away. And again, it's the same thing that kind of forms that nice patterns in Saturn's rings. The same thing happens in our asteroid belt, and that's probably why it never formed a planet between Mars and Jupiter. So the Kirkwood gaps in the asteroid belt, that's what gives that asteroid belt an interesting structure that I've shown you. It occurs at distances from the sun such that the period, meaning how long it takes an asteroid to orbit the sun, would be a simple fraction of Jupiter's orbital period. So if it's 1/3, that would mean for every 3 orbits of that asteroid, you get 1 orbit of Jupiter. Or for every 4 orbits of asteroid, you get 1 orbit of Jupiter. And so on. Here's a poll question for you, but I'll basically answer it for you. Why are there very few asteroids beyond Jupiter's orbit? So recall earlier in the course, right, we talked about the frost line, right? We talked about past the orbit of Jupiter, it was cold enough in the early solar system for ices to form, right? And so that's what actually formed all these large dwarf planets. Remember, after dust, rock, and gas, the next largest thing in the solar system was ice. So all that ice formed huge ice balls, right? And that's what originated these large planets in the outer solar system. So past the orbit of Jupiter, you still have plenty of asteroid-like rocky material. It's just you have way more ice. So all of the asteroid-like stuff in the outer solar system has lots of ice mixed in it. So we call these comets, not asteroids. So I'll ask you a question. Why are there very few asteroids beyond Jupiter's orbit?
What the heck you got a comb for, huh? To cut your hair?
Okay, I'll give you 5 more seconds. Okay. And right, so the majority of you got this, although I really did just kind of give you the explanation. So I'm surprised that so many people said that there was no rocky material beyond Jupiter's orbit. Well, no, I just said that there's plenty of rocky material beyond Jupiter's orbit. The reason why we say there's very few asteroids beyond Jupiter's orbit is because there's a lot of ice outside Jupiter's orbit. So all that stuff out there that we would call asteroids, there's lots of ice mixture. And that's what we call comets. By the way, before I go any further, since I do have people's attention because we just did a poll, I do actually want to give another poll, but one that is not asking you to know anything about the content of this course, but I'm actually curious to know about your thoughts about fall. Whether or not you're going to be here in the fall, I'm curious whether you would most prefer that things went back to face-to-face, because this is a discussion that people are having in the administration. It's not something I have much control over, but I'm curious, right? Like, would you all prefer to go back to in-person normal classes, or do you prefer remote instruction? So hold on, let me. And this is assuming that we have coronavirus under control. So let me, just because I'm curious, what would you prefer in an ideal world? Okay, give you 10 more seconds to state your preference. Okay. So I'll share it just for your curiosity. Seems the majority of people would prefer in person. Okay. Thank you. And there's a couple chats here. All right. Any questions since we're at a stopping point? So. All right. Okay, so before I move on to a slightly different topic, I do just want to mention, so most of the asteroids are in the asteroid belt. But there is, and most of the stuff outside the asteroid belt, past Jupiter, is more ice rich. We'll call those comets, which we'll talk about in a second. But there's a few stuff much further away in the Oort cloud. And actually, it was only recently, relatively recently, that the very first interstellar, meaning coming from outside our solar system, asteroid was discovered. Okay, it's called Oumuamua. It was discovered in 2017. Here's a pathway through our solar system. So it's an example of what we would call a hyperbolic trajectory. So not an ellipse. Well, it's a conic section, but not a circular shaped ellipse. It's called a hyperbola. And week by week, it's showing its trajectory as it passed kind of from above our solar system down through the orbit of Mercury, and then back out again. and it went on its way. There was some speculation, still is some speculation that it could have been a alien spacecraft or something. I mean, no one knows. It's pure speculation. But it was kind of it's the very first interstellar asteroid like object that we've seen, and we can't get a good photograph of it because it's remember, the only way we can see these things with these beautiful photographs I showed you is if we send a dedicated mission out to look at it. Otherwise, we just kind of all we can see is this little point dot in the sky, pretty much. Because we don't have much information about this other than it's the first interstellar asteroid. It's kind of an exciting thing to consider, right? That the reason why some people speculated it could be an alien craft is because it had a shape such that, as far as we could tell, it had a shape that was very kind of oblong, and it appeared to be changing color to such a degree that it had to have a really extreme shape that suggested maybe it was using something like solar sails or something. Anyways, it's mostly speculation, but that's the only interstellar asteroid I'm aware of. Now, on the other hand, we have very nearby asteroids that create meteors, and then also mostly debris from comets produce meteor showers. So let's talk about that. First of all, terminology. When you hear meteor, meteorite, sometimes meteoroid, they have real meaning. So a meteor, right, is technically is the name for the flash of light, right? When you look up in the sky and you see that flash of light, we call that a meteor. Whereas meteoroid is the term for like the thing that became a meteor. And then if that hits the ground and you dig it up, in other words, something that survived the passage through the Earth's atmosphere, we call that a meteorite. Okay. Most meteorites we find dig up are from the asteroid belt, as you'd expect. But we actually find some from the moon, some from Mars. That's because the moon and Mars are impacted by stuff, and then some of that debris ends up making it to the Earth. Here's the largest example in North America, giant iron meteorite in this case, 32,000 pounds, more than 10 feet tall, mostly iron and nickel. So this comes from something that's what we call differentiated, meaning this is like the iron core of a planetoid originally, something that differentiated because it was so massive and hot in the early solar system that all the iron and nickel sank to the bottom. Okay, we see a chunk of that core. Made it through our atmosphere, and it planted itself in Earth's soil that someone dug up. So the name for this is primitive versus processed. That is, some asteroids are processed, meaning come from something that's differentiated, like this thing I just showed you. So it's just a piece generally of a larger asteroid that broke off its core or its mantle that's processed. But then there's also primitive, meaning this is just stuff from the very early solar nebula, little clumps of rock and flakes and stuff that kind of formed a rubble pile, essentially. Okay. So primitive and processed are the two largest categories of meteorites that we see. Okay, here's an example of what you see when you have a fairly primitive meteorite, is that it's kind of a bunch of rubble, right? That was kind of squished together. Okay, so you see something that looks like this. So you have a lot of little pebbles and stuff kind of compressed.
Looks pretty.
Rocky-ish. Okay, so we call those little circle-like, pebble-like things, we call those chondrites. So meaning pieces of an undifferentiated, unprocessed, unmelted body that kind of compressed together under gravity. This is actually the origin of most meteorites. The other main types are achondrites. That's a stony meteorite that doesn't quite look like this. And then you also have iron
Not both
meteorites that are
dirty
also
yet.
iron core, iron and nickel. And then you also have kind of in between, stony iron. Sometimes you have bits of iron and stone together. And we do see on Earth meteorites from Moon and Mars. Actually, I mean, there's this whole question of when you see something on Earth, how do you know whether it's a meteorite? I have a link here if you click on it to help guide you if you do. But how do we know, right? So yeah, you look at its composition, right? You compare it to the composition of the Earth. You look at the isotopes. So we talked some about isotopes. Now, if something is sitting out in space for a long time, it gets bombarded by cosmic rays that because the Earth protects us from a lot of things, right? Because we have an atmosphere, because we have the ozone layer, we have our magnetic field. So actually, because they get bombarded in outer space by cosmic rays, they develop different isotope ratios, so we can tell. And also, if you have a meteorite that we find on Earth, it went through our atmosphere and it got really hot on the outside. So we see evidence for that. It has a melted outside. Okay? So we have ways of knowing. And here I have a plot just showing the composition. So there are characteristic compositional differences between like the mantle of Earth, or the crust of Earth, where we dig up rocks and stuff, compared to stuff from asteroids. So here is a plot showing the amount of iron oxide and magnesium oxide as a percentage compared to aluminum oxide. And what you see is that Earth materials on the lower left of this diagram, whereas, for example, stuff from the moon falls on this line. And we compare this to the stuff we actually took from the moon and brought back. So we found over 30,000 meteorites. There's tons of meteorites. People there's meteorite hunters find them every year. And there's about 100 known Martian meteorites, about 100 known lunar meteorites. Here's some cross sections. So here's examples of rocky meteorites here, and here's an example of an iron meteorite. And meteor showers are a particular phenomenon that's a little bit different than just talking about a single meteor impact. Okay, so meteor showers tend to come from actually from comets. So comets come by the Earth, every 100 years, sometimes every 1,000 years, or every 10,000 years. And when they do, they leave behind a trail of dusty, pebbly debris. And when they do that, say they do that every 10,000 years. Last 10,000 years ago, they left behind this trail of debris. They might look like this. Okay? Then every year, the Earth, on its orbit around the sun, moves through that debris field. Okay? And every time, then the same time of year, when the Earth goes through that debris of dust and pebbles, you get a meteor shower. And since you have kind of a stationary debris field, and it's the Earth that's moving.
Over there.
When you see a meteor shower and you take a long photograph, you actually can see this. It looks like
There's a bathroom.
a windshield when you're driving. Amazing, right? It shows you that if the Earth is moving this way, right, the meteors are flying at you this way.
Why you open the fridge? There's no paper in the fridge.
There's the Leonid shower. You see?
Why are you out here?
Flying at you like you're driving through the rain.
Thank you, Haya.
Sitting out there, it's the Earth that's moving through them. So here's just an example, right? Famous meteor showers like the Perseids every August that came from the Swift-Tuttle comet. There's the Orionids every October 22nd, Halley comet, and so on. So as a summary, okay, most meteorites are pieces of asteroids. So I didn't maybe emphasize, but meteorites come from asteroids, meaning they're pretty large, right? In order to make it through Earth's atmosphere, you have to be large enough, and often something like iron, to survive, okay? Meteor showers, those streaks of light you see, they're coming from little pebbles, okay? Even little grains of sand that are burning up in the Earth's atmosphere. They don't usually leave behind a meteorite. You have to have something that's large enough to survive entry through this atmosphere. And kind of amazingly, more than 1 million kilograms of meteorites fall on Earth every year. So we're constantly being bombarded by little pebble dust-sized meteorites. Okay? Okay, so when we talk about a shooting star or meteor shower, those streaks of light we see are from just like a pea-sized particle. And here's a question that I'm not going to ask, but what can meteorites come from? Well, they can come from all of the above. They can actually come from the moon or Mars, right? That's rare, but they can. If the Mars gets hit by something and debris comes out, that debris can end up hitting the Earth. It comes from the crust and mantles of asteroids. It comes from the cores of asteroids. That means it's an iron meteor. Okay? So all of the above. Any questions so far? Okay, so comets, right? So this is the counterpart to asteroids that are further out in the solar system, past the frost line, where you have lots of ice. So these are ice-rich objects. Here's Comet Hale-Bopp. So this is some nice pictures of comets, and we'll talk about what gives them this characteristic visual quality. So these are icy leftover material. So just like asteroids, but there's more ice. Stuff formed beyond the frost line, so they're from the outer solar system. The very, what we call the nucleus of the comet, the thing that's generating that nice tail, we call the nucleus. That's a dirty snowball, basically. It's like it's ice, but it doesn't look like ice. It's dirty, right? And most comets are just perpetually frozen in the outer solar system. For example, if they're in the Kuiper belt, they're just frozen out there. We don't see. They don't have tails. It's only comets that can enter because they have a really elliptical orbit, maybe every 100 years, every 10,000 years, they fall close to the sun, and then they warm up and they develop tails. Okay? Most, because they have to have a really elliptical orbit, they must be coming from the Oort cloud. That is, they don't just sit in that nice belt, because then they would never come close to the Earth. They're coming from these random orbits deep from the outer solar system in what we call the Oort cloud. And so here's an anatomy of a comet. At the very center is the thing that's there before it has a tail. It's called the nucleus, okay? Just an icy dirt ball. Then we have the coma. That begins to shine brightly when you get towards the sun. And that's a cloud of gas and dust, because when that snowball gets towards the sun, it gets started to get heated up. That gas, that ice turns into a gas that creates a cloud of dust. We call it the coma. Actually, also the light from the sun breaks apart the ice into hydrogen and oxygen, and that produces an even larger glow called the hydrogen halo. And then you have the plasma trail. That's that gas from that hydrogen halo gets ionized by light from the sun and gets pushed by the solar wind. So the solar wind pushes it back. That forms a tail called the plasma tail. And then you have a second tail that's just all the like little dust debris that kind of is released as the ice melts. Little debris gets left behind, and that gets pushed in a different direction, depending on the size of the pebbles and dust by light pushing at it from the sun. Here's an example, Halley's Comet. This one comes around every 75 years. So there you see its nucleus very clearly, and then the coma glowing around it, and the tail off to the left. So here's a cartoon just showing what happens. So you have something coming from deep in the solar system, deep far out in the Oort cloud, and every once in a while it starts coming in. Once it gets towards about the orbit of Jupiter, the coma starts to form. It starts to get warm enough that the ice starts to melt and turn into a gas. Once you get about Earth far away from the sun, you develop a tail. And you see you have two types of tails. You have the dust tail. It tends to go in a slightly different direction from the plasma tail. So plasma tail is from the heated up gas. The dust is dust that's left behind. And you even have some debris that hardly forms a tail at all because it's so heavy it doesn't get pushed much by sunlight. Okay, and then as you get far away from the sun, the tail goes away, it starts to freeze up again, the coma goes away, and it becomes back just a cold ice ball back out into the outer solar system for another, say, 100 years or 1,000 years. Here's some more pictures of comets. Comet Holmes. So in the center is the nucleus. See a very nice coma here. Here you mostly see the ion trail in blue. It's Comet Kayakitake. This one, so some of these comets come from very far out in the solar system. This one comes around every 70,000 years. So it's going to be quite a while before we see this one come around again. This was called the Great Comet of 1996. Another picture of it. Here's Halley's Comet. This one comes around every 75 years. This picture is from 1910. So the previous comet I showed you was from 1995. Maybe 85. This is Halley's Comet. Very famous one. Comet Hale-Bopp. Here you have a very clear difference between the ion tail in blue and the dust tail in white. Okay, so remember that we have the Kuiper belt here, but most comets come from the Oort cloud, which is much, much further out. It's close to the edges of the solar system. Because otherwise, you're not going to come close to the sun and develop a beautiful tail. That's only if you have these random motions, meaning you're in the Oort cloud, not in a stable circular orbit in the Kuiper belt. And as such, you can have comets that come every 100 years, but some from really far out. Some come around only every 100,000 years. Okay, so some so comets that are in orderly orbits can be in the Kuiper belt, but most of these don't develop tails because they don't get close enough to the sun. But the Kuiper belt is in a flat plane aligned with the plane of the planetary orbits. It's that belt. They'll orbit in the same direction as the planets for the reasons we didn't talk about before. But all these random orbits with objects go out to 50,000 times the Earth-Sun distance is called the Oort cloud. Okay? That's a spherical distribution, so comets can come in from any direction, right? And can come in since they have such elliptical orbits, they come in very close to the sun, develop very beautiful tails. By the way, this was kind of how we formed these Oort cloud comets in the first place. Is you originally had so here you initially had comets that were closer to the sun, maybe in that nice ecliptic plane, formed just like everything else. But every once in a while, you get very close to a really big planet like Jupiter. So maybe a comet initially had a path like this, but then it knocked into Jupiter. So it's actually the opposite of what the slide previously was an example of. So first you have a comet orbiting around Jupiter, then it interacts with Jupiter, and it might slingshot it out to somewhere in the Oort cloud. Over time, you have these orderly orbits that interact with Jupiter, for example, and get slingshotted in some random direction. That's one of the source of comets in the Oort cloud. Okay, and just like we've had missions to asteroids, we also have missions to comets. We've successfully collided with the comet. This was big in 2005. NASA Deep Impact actually collided with the comet to try to dig up, see what was inside. Rosetta, I've already shown actually something.
So the thing to go class?
Churyumov.
Go tell that thing to go to class.
I think I have, so let me actually get, I have videos. So it's Deep Impact comet. Not sure if this is a video. Okay, that's just showing from astronomy picture of the day. It's showing when we impacted this comet. We could what NASA was looking for was how the comet brightened. Right, it was going to analyze the light curve of what happened after we impacted it. So it's here, 3 minutes after impact, 12 minutes, an hour after impact, and it started to die down by about 24 hours after impact. Here's the Rosetta. picture here. That's Rosetta spacecraft as it's about to land on this comet here, which is kind of a really interesting comet that has
What?
kind of.
I got one more class. Will I leave?
It looks like a collision between two billiard balls that's stuck together to form like a dumbbell shape. I think I've shown this video before, but it's just neat because this is this comet where we actually, so there you're seeing a picture of it. So you actually got a hint of that weird dumbbell shape over here. You see how you're starting to see the two parts of the dumbbell. But this
Can you tell that thing
someone
I'm going to
identified a
class?
tiny little moon orbiting the comet. So the
You
comet's rotating.
next
and
time
EMS
I'm going to class? You next time go to class? Stay in the room.
Here's so landing on this comet, as I
He's
said,
in class. Go in the room.
landed on
Take the charge and go.
on the surface of the comet.
Hey, go.
Ice, but it's dirty ice. So when you
Take
see
take
this
a
white
mask
here,
book
this
and
actually
go.
isn't
Take your
snow.
mask book.
That's white snow. That's actually just the sunlight hitting from the left. But it's amazing, right?
Then get it.
Beautiful landscape on the surface. Oh, and here's a really cool video from this probe. As it was heating up, as it neared the sun, you actually had kind of a blizzard as the ice kept getting liberated from the surface of the comet. It was actually just really remarkable. It's a short video, but I'll keep playing it a couple times. So it's like a snowy Christmas there on on this comet. I think that's just remarkable. So this cliff on the left. Okay, and I showed you the example of the trajectory of the first extra solar or interstellar asteroid that came through our solar system. Actually, also recently was the first interstellar comet. So this was discovered just a couple years ago by an amateur astronomer. So a number of times in this course, I'll show you examples of where non-professional astronomers, people like you and me, can discover things all the time because there's all sorts of large data sets that NASA doesn't have enough people to constantly combing through all these pictures. So an amateur astronomer named Borisov discovered this comet. So it's called Borisov's, well, it's given the name Borisov. And here's its trajectory in green as it passed kind of from the North Pole side of our solar system down and across the ecliptic plane between orbits of Mars and Jupiter in December 2 years ago. It passed away and passed through our solar system, never to be seen again. So another interstellar object. Okay, so as a summary, comets are these icy leftover planetesimals that form beyond the frost line. The nucleus of a comet is a dirty snowball, and these comets, most of them just are frozen in the outer solar system. But some have these weird trajectories that take them closer to the sun, so that every once in a while they develop tails. And also what's liberated is material that can form meteor showers. Comets that are in the plane of our solar system are in the Kuiper belt, but most of the ones you see because of their tails come from the Oort cloud, come from far outside of our solar system and come every 100 years or every 1,000 years or something like that. So I'll get started talking about trans-Neptunian objects. So when we talk about our solar system, there's also a set of stuff past Neptune, where it's sort of the Wild West. It's far away from the sun. It's harder to see things out there. And so we keep discovering new and interesting things. And we kind of categorize them as stuff that's past Neptune. So anything past Neptune, we call it trans-Neptunian object. Some of those are just Kuiper belt stuff. And so this is that belt that includes a lot of comets, right? This includes what we call the Plutinos, a set of objects that include Pluto. It also includes the Oort cloud, right? Stuff outside the Neptune. It includes that huge spherical random set of orbits we call the Oort cloud that most of is made of comet, ice-rich stuff. And we keep discovering more and more. There's more than 1,500 known trans-Neptunian objects. But that's only because it's so hard to see stuff out there. It's so far away that everything's not easy to see. There's a huge number of stuff out there that we're still discovering. Here's one object. It's dumbbell shaped. It's a cool example of another example of two kind of ice balls hitting each other and kind of sticking together. Okay, so the largest known trans-Neptunian objects are shown here. So here's Earth and the Moon on the bottom for scale. Pluto's the most famous, right? Pluto is a large trans-Neptunian object. But one of the reasons why we decided to stop calling Pluto a planet is because we kept discovering more and more stuff that's just like Pluto, including planetoids or dwarf planets like Eris or Makemake or Haumea. But we keep discovering more and more. Some of them are larger than Pluto. And if we graph these objects where the x-axis here is distance from the sun and y-axis is their inclination relative to the ecliptic, you see that there's a tremendous number of objects in what we call the Kuiper belt that are labeled blue. So here's the orbit of Neptune. But then you have a bunch of stuff in this belt, mostly near the ecliptic, that includes some really large objects, such as Makemake and Haumea. Just before the Kuiper belt, we call these the Plutinos. So the Plutinos include Pluto, it's the largest one. But then in this range even further, we call the scattered disk. There's some even larger objects like Eris. Okay, and the characteristic of all of these that make them not a planet is that they are associated with a whole lot of debris that never accreted to form one single object. There's just a bunch of objects out there, and they never kind of cleared the path away from each other. So one thing that to understand is nebular theory explains, that there's a region where there's all these planetesimals that form beyond Neptune's orbit, but they just never accreted to form a planet. Okay, so this is consistent with nebular theory. They're all orbiting for the most part in the same direction, and it's very similar to the asteroid belt. So it's just like the asteroid belt, never accreted to form a planet, but it's ice-rich. So it's comet-like stuff, including Pluto, very ice-rich, basically a really large comet that's just a bunch of debris in a belt. So we don't call any single object that they're a planet, even though some of them, like Pluto, are fairly large. Okay, so I will end today's lecture by mentioning Pluto. Pluto is just a really large comet. Okay, it's smaller than all the other planets. It's not a gas giant, right? Even though all the other planets in the outer solar system are gas giants. It's very icy, like a comet, and it has kind of a weird orbit, like a comet. So it's large, so it's we might want to call it a planet, but we've decided to categorize objects like Pluto that are basically a big comet surrounded by debris and lots of other large objects with it as these dwarf planets. Okay, that is, a planet has to be something that orbits a star, has to be large enough for its own gravity to make it round. Pluto satisfies those first two, but it also has to clear all the other objects from its orbital path. Pluto has not done that. Neither has any of the other trans-Neptunian objects so far. So we call large examples things like Eris, like Makemake, Pluto, we call them dwarf planets. All right, so we'll pick up. We'll finish this next time. And if you have any questions, I'll stay here for a minute. If anyone has any questions, otherwise, see you next week. Or Wednesday. Thank you, Professor.
Thank you, Professor. Have a good one.
You too.